Did you think you got it figured out?
I think I did, but I was hoping we could go over it just because I wanted to make sure. I got the right number of symmetries. I just wanted to make sure that my cycles themselves were correct.
Mhm. Right. So let's see here. Let's see if I can share this. I think one of these does, dozens of tabs is the one. So let me see if I can find it. Which one is it? Ah, that looks promising. Okay. All right. So do you kind of see how, I mean, when you stare at this, you kind of see how you have basically the same shape upstairs as you do downstairs. I mean, I'm thinking of the one that's kind of coming out toward us as being like up, and we're looking that we're like hovering above this thing right now, right? We're looking down on the north pole of the dodecahedron, and do you see that you basically have two of the same things? One that's kind of a pentagon with 5 pentagons coming off of it, and then a pentagon on the bottom with 5 pentagons coming up. You see that?
Yeah.
You rotate the thing and pop them together, right? So you kind of have a turtle shell upstairs, and you have a turtle shell downstairs, and the one is just rotated slightly and kind of popped into place. Okay, so I guess we have a total of 12 faces. Is that right? 12 faces. 5 upstairs, 5 downstairs. I like to talk about it in terms of the 2 turtle shells, right? Does that make sense when I say the turtle shells?
Yeah.
So we have 5 faces upstairs, 5 faces downstairs. We have 5 vertices around the top, around the top pentagon. You have 5 vertices around the bottom pentagon, and then you kind of have this zigzag of vertices going around the middle, correct? So let's see. Do you see this little zigzag pattern or whatever going around the middle,
Yeah.
place where you kind of connected those 2 turtle shells? So what do we get there? Well, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? 10? So we have 5 vertices upstairs, 5 vertices downstairs, and then you have the zigzag vertices around the around the connection between those 2 things. Okay. So what is that? 20 total vertices? Right. 20 vertices, 12 faces. Huh, how many edges do we have? Did you do an edge count? I mean, I'm just trying to bookkeep as many things as we can about this thing. How did you count edges, Katie?
So I pulled up online like a 3D like model thing that I could mess around with, and it just had listed that there was 30 edges.
Okay, yeah, and let's see if we can kind of reason that out. It's just nice when you think through these things, it really gives you a good feel for what's going on. Okay, so you
Well,
have
it seems like
5 vertices around the top pentagon. Sorry, 5 edges. Yeah. And then do you see the 5 edges kind of going down here, 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 and here, right? That's 10 edges with the pentagon upstairs and the 5 going out. And the same thing is going to happen on the bottom. You have 5 and 5, right? And then how many zigzag edges do we have kind of connecting the top and bottom turtle shell? Well, I think it's going to be basically the same as we had before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 zigzag edges going around, 5 upstairs, 5 downstairs. Is that everything? So how many did we have total then? is it 20?
I think it's 30 because you had the 10 on the top, 10 on the bottom, and then the 10 kind of in the zigzag.
Oh, right. 10, 10. That's right. 10 edges upstairs, 10 edges downstairs, and then 10 zigzag edges make 30. And we had 5 vertices upstairs, 5 vertices downstairs, and then 10 vertices zigzagging around. So that's why we had 20 vertices. So 30 edges, 20 vertices, 12 faces. Make sense?
Mm-hmm.
Okay, now let's talk about symmetries. So first of all, in fact, I'm gonna write those numbers down just because I don't want to have to burn my brain to try to refigure these out. So I have vertices, there are 20, edges, there are 30, faces, there are 12. Okay. Okay, so vertex destinations. How many vertex destinations are there? So if I concentrate on like one, let's just kind of concentrate on one vertex, like maybe this one right here that I'm hovering over right now. Can you see that?
Yeah.
If I concentrate on that vertex, okay, I don't know, can I actually annotate on this as it is? Maybe I can. Hang on a sec. Yeah, here we go. All right, so what color do I want? I'm gonna do red here. Okay, so if you concentrate on this vertex right here, and then maybe, oops, what in the world did I just do? Come on now. Okay, and maybe like this edge. So if I just fixate on this vertex right here and that edge, then I just have to think about possible destinations for that pair. Okay, so how many vertex destinations are there?
20.
20. And then how many edge destinations around that vertex destination?
3.
3, right? So it's going to be 20 times 3 possible symmetries at most. But I think we can actually come up with 20 symmetries. Okay?
60,
So like, what symmetries
right?
were you thinking of, Katie?
Well, there should be 60, right? Because 3 times 20?
Yep, 3 times 20. There should be 60.
Yeah.
Yes.
Okay. So if you go straight through the center of an edge to an opposite edge.
Okay. So let me try to annotate a couple of those. So for instance, maybe I'll do it in blue. So, well, how about the edge that's highlighted right now?
Mhm.
And I'll do this edge down here. Wouldn't that be like an opposite edge?
Mhm. Yeah.
Okay.
So there's 15 pairs of those.
Right. That's why it's important to know the number of edges. Yes.
Mhm. And then the only symmetry with that, I mean, other than the identity one, but we'll deal with that separately, is 180. And
Yeah.
that's just going to give you a whole bunch of 2 cycles.
Yes.
So you'll get 15 times x sub 2 to the 10th.
Yeah. X sub 2 to the 10th, because how many pairs of edges are there, or how many pairs of vertices are going to be rotating into each other?
10.
10, right? 20 divided by 2. Right, so
Mhm.
it's important to kind of know the number of edges, vertices, and edges, because vertices, faces, and edges, just because you never know when you're going to have to kind of cling on to that material. So we have 15. Basically, what you just said is you have 15 x2
Mhm.
the 10th, right?
Yeah. Mhm.
That's going to be one of the summands.
Mhm.
Okay, and what other kinds of symmetries did you discern there would be?
So if you go straight through one face to the opposite face,
Okay, yeah.
then you can do rotation. So because there's 5 vertices around any face, and that's
Right.
prime.
So if I put a point in the middle of this face and a
Mhm.
point here, I'll use a different color here. And I do another point in the middle of this opposite face down here. Okay, what you're thinking about doing is like drawing an axis through those two or something,
Yeah.
right? And rotating through those.
Mhm.
Okay. So
Um,
so yeah.
so
And
you can, sorry.
go ahead. Go ahead.
So you can rotate by 72 degrees,
Mm-hmm.
and that'll get you back where you were. And that's going to give you a series of 4 or 5 cycles, because the one at the top is going to all just rotate. The one at the bottom is all just going to rotate. And then for the 10 zigzag in the middle, there's like kind of the higher ones and the lower ones.
Yeah.
And the higher ones will rotate into each other, and the lower ones will rotate into each other.
Right. So for instance, the kind of troughed vertices like that one,
Mhm.
that one, that one, that one, and this one. I think those are all the troughed rotation or the troughed vertices, right? 1, 2, 3, 4, 5, right? That's
Mhm.
form a little 5 cycle. And then the peaked ones, which I'll kind of draw those in pink because for peak for peak. Okay, like this. Those are going to rotate into each other, right? And I can't, how do I move this? There we go. What in the world? Let me do this now. Now suddenly it's not letting me draw anymore. Oh well. You know that this one here is also pink, right?
Yeah.
Okay, so those are going to create a 5 cycle. So you're going to have 5 cycle upstairs, 5 cycle downstairs, and 2 5 cycles among vertices on the zigzags around the edges. It should remind you a little bit of what happened with the icosahedron, right?
Mhm.
Okay, so
Yeah.
so how many of those facial rotations? And oh, and by the way, Katie, do any of those cycles like break down into smaller cycles when you rotate by more than 72 degrees?
No, so you can do that rotation 3 more times.
Mm-hmm.
And I think you mentioned it's because it's a prime, 5's prime.
Yes.
It's not going to
Yes.
break. It's going to, I mean, the order will change, but it will
Huh?
still be a self-contained cycle.
Yeah, that's exactly right. Yes. So it's a different symmetry,
Hmm.
right? If I rotate by 144 degrees, for instance,
Hmm.
a different symmetry, but I'm still going to get a 5 cycle.
Yeah.
Like, you know, if I do 144 degrees, this red will go to this vertex, which will then go over this vertex, which will then go to this vertex, which will then go to this vertex, and then we're back to the beginning. Yeah. So that's still a 5 cycle. You get like a little star. Did you see that?
Yeah.
Right? Yeah, you get a star when you do that. And similar things are going to happen with, you know, 144 plus 72, 216 degrees or whatever it is. And a breakdown into like 2 chunks would imply a factor of 5 that was non-trivial. And that's not possible. Does that make sense? As if we were doing it with a square, 4 does have a trivial factor, namely 2. And that's why you had the 180 degree thing going on, breaking down into 2 cycles.
Yeah.
So all of those, okay, so let's count these things. How many of these facial rotation things are there?
Well, so there's 4 rotations. There's the 72, and then that squared, that cubed, that's the 4.
Uh-huh.
Like row of that. And then because there's 12 faces, there's going to be 6 options for opposite faces.
Yeah.
So that's going to give you a factor of 24 times x sub 5 to the 4th.
Yeah. Yes. So we're really building these things up pretty quick. And by the way, you also have the identity.
Yeah, so that gives you an x sub 1 to the 20th.
Yeah,
Which
X sub
actually, when I
1.
was doing this, I almost forgot about, and then I was adding things up, and I was like, I'm off. And then I was like, oh, wait.
Yeah. Right. So we have, so far we have 1 plus 15 plus 24 symmetries. Okay, so we have 40 symmetries. So, now what?
So now we can go from vertex to vertex.
Right. So let me annotate a situation like that maybe. So okay. So let's see here. Maybe I'll do well, I don't know if I'll do black. Okay, so I'll put the black on the bottom. So like this guy right here. Okay, that would be paired with this guy up here, right? Let's do purple. No, that's not distinguishable enough. Well, I'll just do dark blue like this. Okay, and then basically what you're saying is you're going to draw, oh boy, right? Those you're going to draw an axis through those two vertices right there. Yeah. Yes. And what's the rotation? What's the rotation about those points going to look like?
So you've got a 120 and a 240.
Yeah, that's right. So we're going to have two of those, right? And nothing breaks down since the rotation is of order 3. Okay, and 3 is a prime. You're not going to have some kind of subcycles that form or something by doing 120 versus 240. 240 is basically like going backwards by 120 anyways. Okay. And looks to me like you're going to have a couple of 1 cycles, right?
Yeah, so the one you're rotating through will give you a 1 cycle. So in this case, it's that black one and then the blue one.
Yeah, that's right. So you're gonna have those guys. That's what's going to be happening. And what else? Looks like you're going to have a 3 cycle, for instance, with like this right here, and then you're also going to have that with the vertices on the bottom. You're going to have some a 3 cycle there. And man, what happens with what happens with other vertices?
I think everything else just goes into some sort of 3 cycle, but this was the part I wasn't quite as sure about.
Okay, so let's trace. Okay, so let's think about this. Let's follow the path of like, let's see here. Let's follow the path of like this vertex right here. Okay. And suppose we are kind of rotating like that. And that thing is almost the exact color of that face. Okay. So what's going to happen with that thing? So if I rotate like that, well, oh, that's easy. That thing just goes here. And then it goes here. Tone. Yes. But what about what about this guy? Well, what I would do is I would imagine it kind of being attached to that vertex. Does that make sense? It's probably easier to do that. You know that this guy goes here, right? And so that means that this edge right here goes here. Okay. And so what is that going to tell you about this edge?
It's going to be like right on the one right on top there. Wait, no, I'm looking at this one.
So this edge right here, like if this edge swings over to here, this edge right here is going to swing to here, isn't it?
Yeah.
Okay. And we're going to be right there. And then what? Right, if it rotates again, right, so it's going to go over to here. This edge right here is going to swing to here. Yeah?
Mhm.
Which means that this edge right here is going to swing to here, right? So I would be right here.
Yeah.
And let's just make sure that works out for the next rotation. I think it does. Okay. This vertex here is going to swing to there. Yeah.
Mhm.
And so this edge here is going to swing right up to here. Isn't that right?
Mhm.
So it's a, yes, it's a 3 cycle, and you can almost see that happening. I think that's going to be true no matter what. You could find some path of edges to everything, and just, or either from, you know, emanating from this vertex, a path starting from this vertex to some edge, or to some vertex, a path of edges from this vertex, which is one of the axes of rotation, or one of the anchor points. You can find a path of edges from that one over to whatever vertex you're thinking about, or from the bottom guy. Does that make sense?
Mhm. Yeah.
And I think you're going to be able to see that these things are in like a little 3 cycle.
Mhm.
Okay. So how many 3 cycles do you have?
I
So
think
there's
6.
Did you say 6, Elise?
Mm-hmm.
Yeah. So it's going to be x1 squared x1 squared x3 to the 6th. Yeah.
Mhm.
And the question is, how many of those are there?
20, since there are, well, there's 20 vertices total, so divide that in half since it's going through
Yep.
2 of them. And you get 10, and then there's 2 rotations for each one of them.
Yeah, that's right. Yeah, so there's 20. Yes. So that's pretty interesting. It's probably at least as, I mean, there was another one where we had 60 symmetries. Was that the icosahedron?
I think
I think
so.
so.
That wasn't the cube. No way could the cube be that complicated. I'm pretty sure that was the icosahedron. But yeah, the dodecahedron and icosahedron tend to have pretty similar complication. So we have 60 symmetries here. So the cycle index polynomial, of course, you would take that. You'd have to divide, or you'd have to multiply by 1/60th to finish the job here. But yeah. Does that make sense?
Mhm.
It's kind of fun to mess with.
Mhm. Yeah.
Yeah. All right. Any other questions?
I did have a question about our probability project again, if that's all right.
All right, cool.
Just for, I mean, several of the questions we are kind of referring to a graph of a parallelogram, and I wasn't sure if you wanted us to include that graph in there.
Yeah, I mean, I think that would be helpful. I mean, oh, you mean like, do it in Desmos or something?
Or would it be
Well,
all right if we just like hand drew it and put that?
Yeah, you could, that would
there?
be fine if you hand drew
Okay.
it.
Okay.
Yeah.
because we did have a graph we were referring back to when we
Mhm.
did the calculations, but we didn't know if that should go into the project itself.
Yeah. But so you did find that there was this ever growing like parallelogram.
Mhm.
Yeah. Yeah, sure. And by the way, if you try to do it all at once and don't, I mean, I may have mentioned this already. If you try to do it all at once and don't do it in that stepwise fashion that I'm showing you, your mind just starts to go insane. I mean, you kind of see what's happening in 3 dimensions, But then, of course, once you get to four dimensions, it's like you can't even visualize what's happening anymore. So doing it step by step, you get pictures every single time, which is helpful. But yeah, I mean, I think it would be helpful to have that picture so that you could refer to it.
Okay.
I think for me, I don't know that I would have been able to figure out what the bounds were without that picture necessarily.
Oh yeah, we definitely relied on that, which is why I
Yeah.
wasn't sure if you wanted it in there.
Yeah.
Yeah.
But then once you have the picture, it's like, oh yeah, now I see
Mhm.
what's going on. Why we have to break it up. So yeah. Yeah. So yeah, good question. Sure, by all means. You can draw it in there, and if you want to do that, and it's, I guess, scan the hand-drawn version of the thing or something, that'd be fine.
Okay.
I mean, I think there are ways to, there's probably some piecewise defined thing you could do in Desmos to make it work, but that might be a little annoying. Because that would be in addition to the piecewise things you're already doing in there.
Yeah.
Well, what else?
That was all I had. Yeah, just worked through the cycle index polynomial for that, and I wanted to make sure I hadn't missed something.
Did you guys see the proof of Polya's formula yet?
Yeah.
Did it make sense?
Yeah.
Wow. Okay, cool.
Yeah. I mean, I think I'll have to go do some example, like the homework to really cement it in.
Yeah.
But
I mean, the way I did it's it's pretty different from what the book did. The book basically did an example, and to me, it just wasn't clear why that example generalized. And so what I was trying to do is say, just look at one summand, basically one term in the cycle index polynomial, not even having like here in this one example, you have 24, for instance, right? X5 to the fourth. All I'm doing is saying, no, I'm just looking at X sub 5 to the fourth. I'm looking at what one permutation does. Let's think about it. And I think if you do that, you really see why that substitution gives you the pattern inventory very clearly. So hopefully that was helpful. Yeah, we'll definitely do some examples next lecture. But that's the theorem, and you should be able to probably do the homework now for sure from 9.4. Well, what else?
yeah, that's all I had.
Okay. Well, thanks for popping in.
Yeah, thanks so much.
Thank you.
Yeah. Have a good rest of your day.
You too.
You too.
See ya.
Bye.